Welcome to another video. Today's video is the first one in talking about duality. So first topic we're going to talk about with duality is what the Hillier textbook calls the fundamental insight of the simplex method. So let's think about a linear program in matrix form. So looking at this matrix, sort of see that those are the coefficients of the objective vector. And so we'll call Z our objective value. These are going to be the objective coefficients. And we can collect them together into a vector that we're multiplying by our X vector. X is our variables. And so A times X, that A is the constraint matrix. And then the B is the right-hand side, essentially the limits of each of the constraints. And so typical maximization problem in standard form, we're with less than or equal to constraints, and then each of our variables is constrained to be non-negative. Okay. Once we introduce slack variables, this is the starting tableau for this problem. So kind of labeling the columns, this first column will be for Z. This is actually a chunk of columns, several columns, and those are all the columns corresponding to our original variables. These columns here, and there's going to be several of them, those are all the columns that correspond to our slack variables. And then this here is our right-hand side. Okay. And then we could, I guess, think of labeling the rows. This top row that I've got put here, that's the 0th row, the row 0 corresponding to the objective. And then all the rest of the rows, and this is a whole matrix here, so there's usually m constraints, and so this part here actually represents all the other rows, and those correspond to our basis, and we'll sort of abbreviate all the variables that are in our basis as x with a subscript of b for our basic variables. Okay, so this is our initial tableau. And then what normally happens in the simplex method is that we choose an entering basic variable and an exiting basic variable. And then we do row operations to change from this tableau to another tableau. And when we move to another tableau, we always make it so that our basic variables have the standard basis vectors showing up in those columns. Okay. Well, the elementary row operations that we use to move from this tableau to the next tableau, we can think of that as actually multiplying on the left by a matrix. Okay. And so when we choose our basis, remember we always have Z in our basis, and then all the columns that correspond to our basis, we'll call those XB, representing all the variables in our basis. If you were to take those columns out of this tableau up here and collect them all together into a matrix, and this will have m plus 1 columns and m plus 1 rows, because there's m basic variables, one for each constraint, as well as the Z kind of is the bonus basic variable that's always there. Okay, so we take the columns of the basis, collect them here. We've called B our basis matrix. These are the columns of A and potentially of I that show up in the basis. Negative CB. So remember, when we get our objective, we've got Z equals C transpose X. But we want to get all of our variables onto the right, to the left side. And so we switch this to be Z minus C transpose X equals 0. And that's why we got a 0 right here at the beginning. So we get the negative coefficients showing up in the top row. And then any of the basic variables, they're either original variables, and then they'd have sort of a negative whatever their original coefficient was, or if they were slack variables, they started off with 0 as their coefficient in the objective row. And so this CB is the negative coefficients of the cost vector. That's the objective vector corresponding to the basis. Okay. And if it's a slack variable in the basis, it's got 0 for the initial cost or for the cost vector value. Okay. So what we need to do is when we do our row operations, we change all of these columns to the standard basis vectors. Okay. So 1, 0, 0, 0 and 0, 1, 0, 0, 0 and so forth. Okay. Where there's only one in each column and yeah, and whichever row that one ends up in is the row that corresponds to that basic variable. Okay. So what we need to do is essentially turn this into the identity. Okay. And if we want to turn a matrix into the identity matrix, we need to multiply by the inverse of that matrix. So there are some nice formulas for how to do an inverse of a block matrix. So this is sort of a matrix of matrices. So this B is a full matrix here. There's some nice formulas out there. I'm not going to drive them, but I'll essentially show you what the inverse matrix is in this case. And so if we think about, here's the matrix we're going to use, and we want to multiply by 1. This is actually a 0 vector. Here's a negative CB transpose and B. And we want to choose a matrix here so that we end up with a 1 here, a 0 vector transposed, essentially a 0 row there, a 0 vector here, and an identity matrix there. That's our goal. Okay. And so let's choose something that's going to get us there. We're going to need a 1 here, a 0 here. To get rid of B, we're going to need a B inverse here. And then the tricky part here is that we multiply by CB transpose B inverse. Okay, let's verify that this, when we multiply these together, gives us this. So when multiplying block matrices, it's almost as long as the blocks are sort of consistent with each other, it's just like multiplying matrices. So I'll multiply first row by first column. And so 1 times 1 and this times the 0 vector, that will give us 1 plus 0. And that's not a vector, that's just a number. Okay, and so that gives us the one that we want. That's good. Let's do this row times this column to get this entry over here. And so we get 1 times negative CB transpose is going to be negative CB transpose. And then we'll get plus this times B. And so CB transpose B inverse B. Okay. Then let's do this row times this column. So 0 times 1 plus B inverse times 0. And that's going to give us a 0 vector. 0 vector plus another 0 vector. And then finally, we'll do this row times this column. And so 0 times negative CB transpose is going to give us a 0. Technically, it's going to give us a 0 matrix. But then we'll get plus B inverse times B. So sort of a 0 matrix plus B inverse times B. Okay. So 1 plus 0 is 1. That's what we want there. We get a 0 vector here. That's good. Up here, B inverse times B is the identity matrix. So that essentially disappears and it leaves us with negative CB transpose plus CB transpose. And those will then cancel each other out and give us 0. Finally, down here, we got 0 plus B inverse times B is the identity. And so 0 plus the identity is just the identity matrix. So this is going to be, this is our inverse of this, since they multiply together to give us the identity matrix. Okay. So now what we want to do is our row operations are equivalent to multiplying on the left by this matrix. So Let's go ahead and do that. And let's take our initial tableau, our initial tableau and multiply on the left by this matrix. So we'll have the matrix 1, CB transpose B inverse, and 0 and B inverse. And we want to multiply by our tableau. So 1, negative C transpose, 0 transpose, and 0. And then a 0 vector, A matrix, identity matrix, and a right-hand side vector. Okay, let's go ahead and do that multiplication. We'll do the top row first. Using the top row of here and then multiplying down each of the separate columns there. And so this times this will give us 1 times 1 plus this times 0. That times 0 will cancel that out. And so we'll get just 1. Now let's do this times this, and we'll get 1 times negative C transpose is negative C transpose plus CB transpose B inverse A. And then we'll do this times this, 1 times 0 plus this times the identity matrix. Remember that the identity matrix is like multiplying by 1. It doesn't change anything. And so that times that will give us just CB transpose B inverse. And then this times this will give us 1 times 0 plus CB transpose B inverse B. Okay, that's our top row, our objective row. Now let's go ahead and do the bottom row. So we're multiplying by 0 and B inverse. 0 times 1 is 0. B inverse times 0 is 0. And so we get 0 there. And that corresponds with what we expect. We expect the first column that corresponds to our Z to always be 1 followed by zeros. Now we'll take this times this, and this 0 will essentially zero out everything in the top row, and we'll be left with just B inverse A. And then this times this will give us just B inverse. And this times this will give us B inverse B. Okay, let's label those columns. So this is going to be all of our original variables, X. These are all our slack variables, and this is our right-hand side. Okay, let's call out and label what these are. Maybe I'll go ahead and kind of draw separators in here and think about what each of these are. Okay, so first off, kind of thinking through this is what we'll notice is we get B inverse right here. And so if you're doing your row operations, the B inverse matrix is the matrix directly under your slack variables. And so I'll say this is going to be useful later on, and that we can always find our B inverse matrix after doing our row operations and know what is that B inverse matrix. Okay. Here is the right-hand side. And it's the right-hand side, and it's the right-hand side after transformation. And if you think about what we do, that right-hand side tells us what our current solution is for our basic variables. And so we're going to call this XB. It is the value of our basic variables at our current solution, right? And then remember, all of our non-basic variables are set to 0. So this is essentially our current solution. It's going to be a vector that's not quite long enough because it will only have the basic variables in there, but all the other variables are then 0. Okay. Let's introduce this quantity here. So underneath the slack variables, this quantity here, we'll call this Y transpose. And these are what we call the dual variables. We're going to talk about duality in just a bit. These are the dual variables. They have a little bit of a interpretation as shadow prices that we'll talk about in just a bit. Um, and yeah, so we can kind of abbreviate essentially the quantity CB transpose B inverse as we'll call that Y transpose. It's going to be the values in the objective row beneath the slack variables. And we'll talk a little bit more about what those mean in a little bit. Okay, let's look at this value here. This is the current objective value. Okay, and so if we take the costs or the objective values corresponding to the basic variables, we multiply it by B inverse and then by B, our right-hand side, we get our objective, current objective value. But we just introduced the fact that we're calling this quantity here our Y transpose. And so we can think of this as also Y transpose B. So if we take these dual variables and multiply them by our original right-hand side, that gets us our current objective value. Okay. And then maybe the last thing I'll point out here is the objective row value underneath our original variables. So this is going to be, let me actually relabel this as being Y transpose because we see another copy of that CB transpose B inverse. And so this is going to be Y transpose A minus C transpose. Okay, these are called reduced cost. Of the original variable. Sort of thinking of they had their original cost is this negative C transpose, and then it's reduced by whatever Y transpose A is. And we'll talk a little bit about what that means in a little bit later on too. Okay. This, it's optimal, our current basis is optimal if Y transpose A minus C transpose, the quantities underneath the original variables there. Let me slide this up a little bit. It's optimal if all of those reduced costs are greater than or equal to 0 for for a maximization problem, as well as we also need the values underneath S to be greater than or equal to 0. So we also need that Y transpose is greater than or equal to 0. Okay, so our tableau or our basis is optimal exactly if this condition holds and this condition holds. And if you look at that, that almost looks like constraints for like a non-negativity constraint on my dual variables, as well as another constraint involving my A matrix on my dual variables as well. So interesting, and that's going to be essentially the heart of duality in just a second. That's it for this video. In the next video, we'll talk about shadow prices.